Hi there, everybody. Mr. Wisher here. Wanted to put together, and I'm really trying to make these quick videos, just real fast breakdowns of uh, important categories and big concepts about the periodic table as we are starting this very important journey into really more hardcore chemistry topics about how atoms are structured in relation to how elements will want to bond with one another, the kind of bonds that are made. Um, Lots of different, so many different things that are hidden in the periodic table, we can't even remotely start scratching the surface. We are going to dig into some of them during chemistry this year. But to start with, you got to start with these basics. And as Ms. Harris took you through just basic atomic structure, reviewing just essentials with protons, neutrons, electrons in a little bit more detail, I'm going to hit just metals, non-metals, metalloids. Because basically, as we're looking at the periodic table, and let me just zoom through real quick here to show you. This was the lovely, beautifully shaded table that I was throwing up during the Google Meet that I now know that you could probably hardly see. Next time, I know that I can actually zoom because I can do stuff like that, and that's pretty handy. So this is how we learn things. But in this periodic table, and all the lovely, beautiful shading that's taken place, you can see one of the most general large-scale breakdowns of categories that are found in the periodic table, and that being metals, non-metals, metalloids. So as I mentioned during the presentation, clearly, and I still am screwing up where I'm doing that then, clearly the majority, as you can see here, yep, including our interesting little block on the bottom that's pulled out for some reason, which we will discuss later. Most of the periodic table is metals. A smaller amount here are non-metals here, kind of in the upper right side, and our transitions. So with every, as I mentioned, with every type of substance that has a certain set of characteristics, as we move across and transition from metals to non-metals, you will pass through a transition zone. And these are metalloids. And that's because when we look at characteristics, they show characteristics of both metals and non-metals, which, as I mentioned earlier also, can be super, super helpful in designing certain products and substances. So, very quick breakdown. When you think of metals, you're probably already going to conjure some of these things up in your head. There's going to be images that pop into your mind. If I asked you to list characteristics, you could probably actually hit a lot of these. But these, like I said, are on the very basic side, just to get us going. So all of those metals, the bulk of substances on the periodic table, things that all metals have in common typically are that they are fantastic conductors, which means they allow the passage of, they transport heat and electricity. Now, those two are different things. Heat is energy. Electricity, we're talking actual passage of electrons, particles. Now, physics people out there that get into the duality of, electrons, particle, wave theory, all this fun stuff, we're going to go with particles right now with our subatomic particle world we're dwelling in. But you know this because in the olden days, before they made all these frying pans with these great handles for safety, and they've been doing that a long time. But if you ever didn't have a nice, rubber safety handle on a frying pan and it was on the stove, if you happen to grab that while it was actually heated, you would get a really nice burn because metals transmit any heat they absorb very easily and very efficiently throughout that substance. So they are really effective conductors of heat in the form of heat energy. We will study heat energy further in the course later as well. Electricity is the flow of electrons, and metals are outstanding conductors of electricity, which is why we use our copper for our dominant wiring. It is very effective at being able to get electrons from point A to point B in the form of electricity to be able to power all of our lovely devices that we need. That just means that electrons pass very, very easily through that substance. Insulators would be the opposite. They don't like energy to travel through them, but our metals, like our wiring, copper wiring, great conductors of electricity. So that's why we choose to use copper as our dominant wiring metal. Now, in addition to being able to transfer heat and electricity very, very effectively, they're also very malleable, which means they are shapeable. They tend to give in to the will of being hammered, moved, pounded on, and being able to assume a shape we'd like them to. They are malleable. They will bend to our will more often than not in terms of being able to shape them. So if we put them in a hydraulic press, we can take metals and be able to form them as we wish to make, all of our products that are made out of metal. Non-metals, not so much, as we will see, but that malleability also makes them very effective if we want to make products with them or things like that. But metals are shapeable. Ductile or ductility means they are easily able to be stretched into wires. So that is very important for us in terms of using them to conduct electricity. Being able to make these wires lets us, in a very efficient way, a space-saving way, be able to get energy from point A to point B. But we're able to do that because metals have very high levels of ductility. We're able to stretch them into wires. So what do they look like? Generally, most are solid. One is not. At room temperature, I should say. And they're shiny. So this word luster, near and dear to my heart, as the geology lover that I used to be, geology, earth science, and astronomy, etc., geography, all of them, love, love, love. But we used to use the word luster to describe how shiny something is. So instead of saying, man, that metal's shiny, we say it has a high luster or a high degree of luster. How much does it reflect light? Metals tend to be high. So when you see them, they tend to be shiny. There we go. And that is luster. So you probably could have already thrown out that one. Now, as far as solid goes, yeah, all our metals are solids, except for here we have our lovely mercury. Super fun to play with and mess around with in the olden days, because it just fascinating substance. But we now know that if you mess around with it too much and it absorbs into skin, it is toxic and it can cause some neurological, very unpleasant effects, which is how a lot of substances are, that we'll discover something and we think, oh, this is a fantastic product, and we use it for so many things. Then we find out, as we advance, years later, that that was not a great idea. It only caused 16 different major problems. And so then we have to eradicate, not use it again. Think of lead. In terms of lead was a wonder product, and now not so much. But mercury, also, we will not find it in our thermometers anymore. If you come across it in schools, you have to have that disposed of properly, considered hazardous. But it is really cool in terms of being a liquid metal at room temperature. Sure, watch any good either reality blacksmithing show or Game of Thrones or something. You'll see plenty of molten metal in terms of, or I was about to go Lord of the Rings too. Anytime you're making those weapons, you'll see lots of molten metal. You heat these metals up enough, you'll get melted metal, and we can blend them, make stronger substances. Steel, for example, being alloys. But on their own, we have solids at room temperature, except for mercury, which is Hg, should we call. Now, let's compare to nonmetals. Very quick comparison. Take everything that we just saw in metals and let's do the opposite. Okay, not very far off there. So they're on the other side of the periodic table to the right, upper right dominantly, and as opposed to being great conductors of heat and electricity, they're very bad conductors of heat and electricity. So they will impede heat and energy moving through them, and they will also not do an effective job at allowing electrons to move through that substance and being able to transmit that electricity from point A to point B. So we do not choose nonmetals as our circuitry. And that's because a lot of them are gases too. So think about having wires made of gas. You can do the math here, or do the concept math here of why they're really poor choices for these kind of functions that we use metals for. But instead of mounting the campaign of why you don't want to use them for wiring, we're going to back up and think of the bigger issue of that will come into play later of they don't conduct electricity very effectively, and they don't transfer heat, so keep that in mind. As far as states of matter, most of them are gases, not all, definitely, but most are gases. And if they aren't gas and they're solids, they tend to be brittle, so they tend to shatter. So you can pulverize them, powder them. If they're crystalline here, they'll chunk off, they'll split off. So they're not the large, sturdy structural types that metals are. They're not malleable, which means if you try to shape them using a hydraulic press, they'll just pulverize. So very different texture in terms of our solids, those that are solid. I believe this is sulfur probably right here. Very yellow and very stanky. So if you smell something that smells nasty, usually there's sulfur associated. And if you want to go to Yellowstone and you see those awesome hydrothermal vents, you'll see these yellow, beautiful colors, but this yellow ring that's surrounding a lot of these geothermal areas. And that's from high sulfur content that's coming up from below through sulfur dioxide that's trapped down under the earth. But really beautiful stuff, when you see the colors, but stinks too. So there's your solid sulfur. So solids, brittle, mostly though gases, so are nitrogen, oxygen, fluorine, chlorine, bromine, iodine, hydrogen, running through helium. All of our diatomics, those elements, those gases that love to be in pairs. So you'll always see O2, N2, I2, F2, Cl2. All of our big name gases. So basically, nonmetals, probably what you pictured. Metals, probably what you pictured. The only difference is realizing that you're much more likely to be able to have some examples of solid nonmetals as opposed to only one example of a solid metal at room temperature of mercury. So last but not least, let's just blend them. Metalloids, those are our stair steps. So this is if we're transitioning from the shoreline as we move from one type of substance to another, from our metals to our nonmetals, we will have a blend through of different characteristics that can resemble partial metal and partial nonmetal. That is specifically exactly what metalloids are. So you'll see a lot of periodic tables that have this dark, bold stair-step line, and you'll see that everything that kind of touches that stair-step line here we call metalloids. So characteristics of metals and nonmetals, all of them are solid, and they're all semiconductors, which means they are not awesome conductors of electricity. They're not awful conductors of electricity. They are decent conductors of electricity. And so instead of that being the huge average story, That is really helpful because in electronics, silicon microchips, things that are powering very sensitive devices that you don't want a super huge hot amount of electricity to push through, these are super helpful because they will allow enough electricity passage and current to be able to power devices, but not to burn them out. So when you've got the delicates and you want to have some just good enough conduction to be able to make your product come to life and work, that's what you want. You don't want it too hot, you don't want it too cold, and these semiconductors, Goldilocks style, are just right. So there you have it. Here's our metals, non-metals, metalloids, as we saw, metals, non-metals, metalloids. So again, we will get to our little mystery groups here in terms of what's up down here. Things will have a meaning, don't you worry. Because as we start moving on, we'll start getting into more complicated phases of periodic table breakdown in terms of groups. So our columns are going to be groups. Our rows are going to be periods, and we'll see that shortly. Just for trivia kicks and giggles, I am a super nerd for the history of scientists that make these discoveries, because I've been absorbed with periodic tables for years now, and I've taught periodic tables for years, except you have to step back and realize there was a point in time where that didn't exist. And Dmitry Mendeleev, one of my top all-star fan scientists in terms of creation, Rosalind Franklin with X-ray crystallography and her role in DNA structure discovery being number 2. I wanted you to see this is what the periodic table first was born into as an idea. So this was Mendeleev's about 1857-ish. So we live in a time where we just get to look at a periodic table and there it is. I was born with it. The only thing that's changed is this is a little old. We have filled this row. These now have names because we've made them stick around long enough to be able to earn a name for them. But basically, this is what I've known. I look at it, and it's numbered correctly. It's numbered after protons, which is the correct particle to actually number and identify elements with. And I've learned a lot of patterns of the why of where things are. All Mendeleev was seeing was in all the substances they were working with, and they did some really good chemistry in that era. So it's not like it was, alchemy in a basement just making things poof. They were doing very detailed analytical chemistry. Problem was they did not have a roadmap as to how things behaved and the exact whys, and they had many fewer elements to be able to work with. But the ones they could work with, Mendeleev was observing things tend to react in trends. You see one thing react a certain way, and you'll see another element react in a similar way. And over time, when you react enough and you do enough experiments and you repeat and you observe, you start seeing trend-worthy possibilities. And so Mendeleev just started documenting things where he thought he saw trends appearing. And it was the birth of periodicity, repeating characteristics. So he'd notice, I see these things that are kind of sharing progression in a kind of a regular mathematical way. And then it's like it resets and our other substances kind of keep going in that progression. That's a huge amount of work to be able to come up with those ideas. We take it for granted that it's always been around, but no, somebody had to come up with these ideas. And sometimes it's a few somebodies at the same time. But I just wanted to show you that, no, all this lovely stuff you're learning here, it had an origin story. And it had a human behind that origin story that I particularly like. So who knows years from now what great discoveries some other teacher might be doing laser pointing, streaking stuff on. Years down the road, it might be something you discover. Why not? Why not you? Something that you wrote on a napkin once about a fantastic idea that you had or things that you were noticing in research. Go save the world. Let it be you. Cool. So that's our metals, non-metals, metalloids, and more. Take care.